In this video, we will discuss 10 useful ESP32 features with real examples. That'll level up your projects fast and help you go from beginner to pro way quicker than you think. Without further ado, let's start with... The first thing you need to know is that the ESP32 isn't just a regular microcontroller. It actually has 2 processing cores. That means it can literally do 2 things at once. For example, you could dedicate one core to handling Wi-Fi and the other core to reading sensor data so your project runs much smoother. This is a huge advantage over boards like the Arduino Uno, which only has a single core processor. Please note that by default, the programs are run on Core 1. In this project, ESP32 is blinking the LED with 1 second delay and reading LDR sensor values running on different cores. On the serial monitor, you can see which core is performing which function. The task 1 is LED blink running on Core 0, and task 2 is getting LDR readings running on Core 1. Because each task is assigned to its own CPU core, both tasks run independently and simultaneously, without interrupting each other. If you'd like to try this out step by step, we've added a tutorial link in the description. You will find relevant, helpful links for other concepts as well. Most people only use the ESP32 with a single loop function, but here's the secret. Under the hood, it actually runs on FreeRTOS, a real-time operating system. This lets you create multiple tasks that run independently, instead of cramming everything into one loop. Now you might be wondering, isn't this the same as interrupts, or just using both cores? Not really. Interrupts are quick reactions to events, and dual core only gives you 2 processors. FreeRTOS is like a task manager. It schedules tasks and switches between them so fast it feels like they're happening at the same time, even on a single core. And when combined with the ESP32's dual-core architecture, it becomes really powerful. Here's a simple demo. I created 3 FreeRTOS tasks. Task A blinks the red LED every 1000 milliseconds. Task B blinks the blue LED every 2000 milliseconds. Task C blinks the yellow LED every 3000 milliseconds. Now all 3 are running on the same core. No dual-core use, no interrupts as you can see in the program as well. ESP now is hands down the best feature you get with the ESP32 board. It's a communication protocol developed by Espressif that lets multiple ESP32 boards talk to each other directly, without Wi-Fi, without a router, and with extremely low power consumption. Here's a simple demo using just 2 ESP32 boards. The first ESP32 reads analog values from a connected potentiometer and sends them to the second ESP32 using the ESP Now protocol. The second ESP32 receives the data and adjusts the LED brightness based on the received value. There's no Wi-Fi connection here, no router, no pairing process, just instant device-to-device communication. And the power consumption stays incredibly low because the radios only wake up for a fraction of a second to send each packet. One of the most popular things people do with the ESP32 is create a web interface to control sensors, LEDs, motors, and more. But the basic web server that most tutorials use is blocking. Meaning, if your ESP32 is busy sending a web page, it can't handle anything else. That's where the async web server comes in. The async server handles all requests in the background without stopping your main code. And when you combine it with WebSockets, you can update sensors, graphs, and controls on your web page in real time without reloading the page. Here's a simple example. I connected a potentiometer to the ESP32 and created a small real-time dashboard. As I turn the knob, the value updates instantly on the web page using WebSockets. No page refresh, no lag. At the same time, I can toggle an LED from the dashboard, and the ESP32 reacts immediately. This works because the async server handles everything in the background, while the ESP32's main loop keeps running continuously. This feature allows you to upload a program to ESP32 board over the air without any serial communication. Here are the steps to do it. First, open the OTA web server example from Files, Examples, and then Arduino OTA. Upload this code to your ESP32 board. Make sure to add your network credentials before uploading. Next, open the serial monitor and copy the IP address assigned to your ESP32. Paste it in your browser. Enter your username and password, both set to admin by default. You can change them from here in the program. After you have logged in successfully, you can directly upload the code from here. But there's a catch. In order to update or upload new sketch over the air, you need to include the previous Arduino OTA code every time. Secondly, the sketch file should be in .bin extension. You can generate the bin version of your program by going to Sketch and export compiled binary. You can now upload the file by selecting it and clicking Update, and it will be running on your ESP32 in no time. You can power your IoT projects for months on a single charge by using the deep sleep mode on your ESP32 board. In this mode, the main cores shut down completely, and the chip draws just a few microamps, perfect for battery-powered devices like sensors or wearables. Apart from this deep sleep mode, there are 4 other power modes that you can set your ESP32 to. Each mode reduces power consumption differently, depending on what peripherals you keep running. You can even compare the exact current draw for each mode in the official Espressif datasheet, which shows how dramatically the power usage drops as you move toward deep sleep and hibernation. But here's the real pro feature. The ESP32 also has something called the ULP coprocessor, or ultra-low power coprocessor. It's a tiny processor that stays awake even during deep sleep to handle simple tasks like reading a sensor or checking a pin state, so your main chip can sleep for hours, while the ULP quietly monitors your environment. Here's a simple demo. The ESP32 goes into deep sleep for 5 seconds, wakes up to send a sensor reading, and then goes back to sleep again. This cycle helps you run a project for weeks or even months on a single battery. Most microcontrollers can only output PWM signals, rapid on-off pulses that simulate analog by switching really fast. But PWM is not real analog. It always needs RC filters, smoothing circuits, and even then you still get ripple. The ESP32 is different. It has 2 built-in DAC channels on GPIO 25 and 26 that generate true analog voltages from 0 to 3.3 volts. This means you can produce clean voltage levels, waveforms, or reference signals without any external components, something you simply can't do on an Arduino Uno or Nano. In this first program, I am generating a fixed voltage between 0 and 5 volts using the PWM technique on Arduino Uno. On the oscilloscope, you're seeing the output of this PWM signal. You can clearly see the pulses and switching noise on the oscilloscope. This is the fake DAC. So there is no fixed voltage generated by the board. Now look at the ESP32's DAC signal at the bottom. I am doing the exact same thing here, but using the built-in DAC. No pulses, no flicker. Just clean analog output straight from the pin. This alone makes the ESP32 incredibly useful for audio experiments, analog control circuits, and anything where you need a real voltage instead of PWM pulses. The ESP32 supports both Wi-Fi and Bluetooth, including classic Bluetooth and Bluetooth Low Energy. But what makes it truly impressive is that it can actually run both of them at the same time. This is called coexistence. It means your ESP32 can send data to the cloud using Wi-Fi, while simultaneously communicating with nearby devices over BLE. That's something you don't get in most microcontrollers. This combination makes it ideal for projects like smart home hubs, health monitoring devices, or industrial sensors, where you might collect data from multiple BLE devices and then send it over Wi-Fi to a server or dashboard. Here's the simplest example you can actually build. The ESP32 connects to my Wi-Fi network and prints the IP address on the serial monitor. And at the same time, it's broadcasting a Bluetooth Low Energy device name in the background. If I open a BLE scanner app on my phone, you'll see the ESP32 appear instantly, even though it's already connected to Wi-Fi. That's coexistence in action, both radios running together smoothly. When you start building real IoT projects, the most important thing isn't blinking LEDs or reading sensors, it's security. The moment your project connects to the internet, security becomes the real challenge. Now let me show you how the ESP32 helps solve this problem using this example. First, the ESP32 connects to Wi-Fi, but before it sends or receives any data, it does something very important. It checks who it's talking to. The ESP has a trusted security certificate stored inside it, which we add in the code. Think of this certificate like a list of trusted authorities, similar to what your web browser uses. When the ESP32 contacts the server presents its digital ID. The ESP32 verifies that ID using the certificate it already trusts. If the identity doesn't match, the connection is immediately rejected. Once the server is verified, the ESP32 performs a TLS handshake. This is a secure negotiation where both sides agree on encryption rules and generate secret keys. From this moment onward, all communication is encrypted. Even if someone intercepts the data, they'll only see meaningless, scrambled information. Only after this secure channel is established, the ESP32 sends the actual HTTP request. Now here's where the serial monitor output becomes really interesting. When you see this message, that's not just a success message. It means the certificate check passed. The TLS handshake succeeded. A secure, encrypted channel was fully established. And this final line saying probably okay is the server's verdict. confirming that the ESP32's connection is secure enough for normal internet use. Now here's why this matters for real IoT projects. If you're sending sensor data, controlling relays, or managing home automation devices, insecure communication is dangerous. Without encryption, attackers could read your data, inject fake commands, or even take control of your device. One of the most underrated features of the ESP32 is its support for DMA, that is, direct memory access. Normally, when you send data to a display, a speaker, a camera, or even fast sensors, the CPU gets heavily involved and your project starts lagging. But with DMA, the ESP32 can transfer huge amounts of data directly between memory and peripherals without using the main CPU at all. This is what makes animations on TFT displays smooth, what lets you play audio through inter-IC sound, and what allows high-speed sensors to run without blocking your code. It's a feature you usually find in much more powerful processors, but the ESP32 gives it to you for free. The two most important areas where DMA shines on the ESP32 are shown below. With DMA handling the heavy lifting, your main cores stay almost completely free.